So let's conclude what we saw yesterday. So yesterday, we said, let's start exploring the dynamics of n equals 4 super Young Mills. We saw it's a conformal theory the day before. So let's start exploring the dynamics of this CFT. If we care about the CFT, we care about the CFT data, which is the dimensions and the 3-point functions. So we started by the simplest observable in this gauge theory, which was getting half of the CFT data, which are the dimensions, right? And this is what we found. We found that the dimensions of physical operators are nothing but the eigenenergies of quantum spin chains. It's interesting because a quantum spin chain is something we are very used in condensed matter, and here we are studying some high energy gauge theory, but it's the result. So the energies, the dimensions of these operators are the eigenenergies of a quantum spin chain Hamiltonian. The map from operators to spin chain was trivial. It is just the fact that we have a trace, so there is an order of fields. And all we did is we map phi1 to degree of freedom m1, etc., phi mj to degree of freedom mj. So I have a spin chain where at each side I have 6 options, so it's an SO6 spin chain. And this is a local spin chain where the Hamiltonian we have to compute, it interacts with spins at position n and n plus 1. I can represent its Hamiltonian density like this to indicate it takes 2 neighboring sites and that's it. And it's local and it interacts on 2 sides just because of planarity. That will be true in any large n theory. It's not special to n equals 4 or anything, right? It's just that as soon as you have planarity, you are going to draw local interactions because the interactions cannot jump because that will be non-planar. And so planarity, just large n, tells you that this Hamiltonian has to be local. So that was a given. And then we asked, so how precisely can the fields get shuffled? And they can get shuffled when we do 2-point functions by studying interactions. And we saw that the most interesting term was this one where the scalars are shuffled, where it acts on the spin chain and gives a different state. And the spins can either be permuted or annihilated and created again. That's the permutation and the trace. And this precise coefficient, a 2 and a -1, came from just this particular interaction. The fact that the interaction vertex is this commutator square. This vertex, on the other hand, came from string theory. It was because it was a low energy limit of a 10-dimensional theory that we have this very particular interaction. And it turns out that the fact that these coefficients are precisely tuned like this, that of all possible SO6 spin chains, we got the solvable one. So we got exactly the one that is exactly solvable. And it's a long story, this wiggly line, that I'm not going to tell you about in these lectures. But there is a big, big subject here. And in particular, after we studied this one loop, for these scalar operators, people generalized in many directions. And now the problem of computing the dimensions, which is half of the CFT spectrum, is solved. So this problem is solved. Now, to generalize it, there are many directions we have to generalize what we did in the lecture. One is, in the lecture, we did scalars. So we should do all the fields, not just scalars. Now, if we do all the fields, instead of having a degree of freedom from 1 to 6 at each side, we have a letter at each side, which is made out of these oscillators, A, B, and C. Right? And so you act on these 2 letters, 1 letter here, 1 letter here, and you get 2 other letters, which are reshuffled. And so the way the Hamiltonian works is very simple. You just take these oscillators, you take this, and you take some from here and you put here, and you take some from here and you put there. How many do you take from here? N1, 2, and you put there. How many do you take from here? N2, 1, and you put here. And then the answer is that the action of the Hamiltonian is just a summation over how many you take from here to here. Doesn't matter of what type it is. And how many you take from here to here, and you sum over those 2 numbers. Times a constant that only depends on the total number of oscillators, on how many jump one direction, how many jump another direction. And then we get the cat after this reshuffling. And this constant was very simple. I wrote it yesterday. It was a bunch of some simple beta functions. Now notice that it's not like you can put any combination of oscillators. In fact, if you look at your notes, at our list of words, you can easily see that the number of A's minus the number of B's plus the number of seats at each site is fixed. Right? You can easily look. If you look at what we wrote, you can easily, so it's fixed to what? Tell me, what number should I put here? If you believe me that it's fixed, you can just take your favorite letter and just tell me what this number should be. What would be the simplest letter with the smallest number of oscillators? Or you can look at the list. Two, right? It's true. You can check the list that it's true. But you can also, but once I tell you that it's constant, the scalar has two oscillators, right? C dagger C, for example. Or F has two oscillators, A dagger, A dagger. So once you know it's fixed, it's obvious that it's two. So you start with some word that has many A's, many B's, many C's with this condition. Another letter here that has many A's, many B's, many C's with this condition. And you move them around. And that's it, and you get this harmonic action. So in the tutorial, you are going to play with this harmonic action, taking this harmonic action, and seeing what kind of spin chain Hamiltonian we get when we restrict not to a subsector of scalars, but to a subsector which is more related to gluons, a different subsector of the theory. And the reason for studying that subsector, I will explain tomorrow. Now, so we got a local Hamiltonian at one loop, and then there are higher loops as well. So one direction is going to all operators, that is this. But the other is not, it's not staying at one loop, but going to all loops. Okay? Now, at all loops, what would happen? So what would happen at two loops? Right? If we repeat the kind of exercise we did in the lecture now at two loops. What would happen to the Hamiltonian? It's still planar, so it's still local, but it's two loops. It's not just one loop, right? So what could happen to this local Hamiltonian?
Operator instead of one operator, like PP.
Exactly. So now it doesn't need to be nearest neighbors. It could be next to nearest neighbor. And so these corrections, so what we write is that we have lambda times the local Hamiltonian plus lambda square, and the Hamiltonian now would be next to nearest neighbors. It could involve 3 local spins giving 3 local spins, and so on. So it's an Hamiltonian whose range is increasing in perturbation theory. And so we get some long range Hamiltonian. Of course, it's long range, but there's still a hierarchy, right? If lambda is small, maybe nearest neighbor, next to nearest neighbor, and next to nearest neighbor I keep, but the other ones I can drop. So there is a range that decays, right? Because it's more and more suppressed with lambda, but the range kind of increases. So we start with a local spin chain, and then it's a little bit less local, a little bit less local, a little bit less local. And as the coupling increases, so this becomes less, let me write like this, ultra local. Right? Because we start, it's really ultra local. It's not like there is some decay, right? We start and it's just ultra local. Only the neighbors interact. Then only next to neighbors interact, right? So it's zero interaction after that. Right? That's what I call ultra local. Local, I would say it's something like decays very fast. Right? So we go from being less ultra local as lambda increases. To the point that eventually, when lambda is increasing, well, to call it a local Hamiltonian no longer makes much sense, right? So then, eventually, we can say that if we think of this object really at finite lambda, I can say it's the Hamiltonian of some 1D system. Maybe I shouldn't call it spin chain if lambda is finite, right? Because it starts to interact still kind of local, but not so ultra local. And so we could imagine that this 1D system, I can think of it as some string. Right? It's just my 1D object, the trace, right? We saw that this trace that we could consider, you could think of it as like a closed loop of string. And so the proposal would be that these energies, if this is correct, if you can think indeed as these very dense diagrams as some kinds of energies of some strings, this should be given by the energies of some string theory. And today, we will see what that some string theory is. So let's leave this space here to see what could this string theory be. But anyway, with integrability, with these exactly solvable techniques, people can order by order and eventually even resum everything. And so this problem is solved. The dimensions are known. So you can plot dimensions as function of coupling. Right? What kind of things do you get? For example, there is one plot that we know is this boring one. It's just an horizontal line. That's if the operator is protected. The operator is protected, the dimension is the classical dimension, and it doesn't matter what coupling you are, you just draw a straight line. But most operators are not protected. Most operators are the non-zero energies of the quantum spin chain. Right? Those start classical plus one loop. So one loop gives you the slope. So this slope here, the beginning of the curve, is what are the eigenvalues of that Hamiltonian. And then there is lambda square correction that bends this curve a little bit, lambda cube, lambda 4, etc. There are all the quantum corrections. And if you were to solve it, this is what you would get. You would get that the energies grow and they diverge as lambda goes to infinity, typically with lambda to the 1/4 power. Okay. And so this would be a theory where if this is a string theory, there are some strings that have some fixed energy and all other strings have very big energy. This is to be a string theory. Okay? Good. So that's a summary of what we have seen so far. Now, so today, the goal of today's lecture is to tell you, is to try to guess what is this string theory. And by telling you what is string theory, I will have an equality between a gauge theory and a string theory, and that will be ADS CFT. That's the duality we are after. Okay, so today we discuss the decoupling argument. Okay, so our basic idea is we want to think of this system in two different ways, either as a string theory or as a gauge theory. So let's think of another situation where we could think of our quantum system in two different ways. Suppose we consider a proton. This would be a heavy proton. And then here is an electron. So a light electron. Now, what happens to the electron in the presence of the proton? How does the electron interact with the proton? They exchange photons, right? So there is a photon being exchanged between the proton and the electron. But that's just one option. There are other things that can happen. They can exchange the photon, and we can emit some photon here. Or they can emit after they interact. This effect, for example, this effect of this emission is what's called the Bremsstrahlung Bremsstrahlung. Something like that. I think there is one more letter here. There are two S's here, I'm not sure. And then A as well. Strahlung, yeah, Bremsstrahlung. Very good. This Bremsstrahlung effect. There are other things that can happen, right? We can have the proton and can interact with the electron, and there can be something like this. This would be a vertex correction. We can have some vacuum polarization effect. This would be some vacuum polarization effect, etc. Plus dot, 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 dot. And at the end of the day, this could tell us questions like, if I have my proton and my electron that's going to be deflected, it will tell us some things about these angles, etc. We would learn how the electron is deflected and so on. In particular, we could compute the potential between this electron and the proton by summing these diagrams. And the potential between this electron and this proton would be something like there would be the Coulomb force, alpha over r. And then you were to start computing these quantum corrections, in particular due to loops of the electrons and so on, and you would get something like 1 plus alpha over 4 square root of pi e to the minus 2 mass of the electron times r, some exponential decay like we saw in the first lecture, times mass of the electron times the radius to some 3/2 power plus dot dot dot. And so here, to think of the electron, let me point out that there are two things we could do. One is, suppose we could compute this potential, the effect of the proton exactly, right? And the other option would be, there's no potential, there's just a proton that interacts with the electron, and we sum over all these possible Feynman diagrams. Okay? And so we have 2 points of view. We can either think that we have the sum of all these diagrams, where we have this, where the electron interacts, or we can say that this is the same as the electron moving in a non-trivial background. By this blob, I mean some non-trivial background. That here, I would say, is encoded in this potential where the electron moves, this Coulomb potential. So it feels that there is something there. And I remove the proton and I replace the proton by a non-trivial background. And so this I would call the field theory picture. And here, this electron, this would be the analog of some kind of gravity picture. Of course, there's no gravity in this picture, but you understand what I mean, that there is some background that the electron moves differently because the background is not just empty. And this would give us a flavor that there is these two pictures that we can think. We have A, that would be the analog of n equals 4 super Young-Mills, where we have some field theory and we sum over all possible interactions. We start at 1 loop, 2 loops, etc. That's the kind of things we were doing there. And we could ask whether there is a new description, B, and the equality between the two would be this duality we are after. So that's one kind of idea we could pursue. Now, for us, here, instead of a proton, we'll consider another heavy object. Right? Here, what's important is that the proton is heavy, right? And instead of a proton, let's consider a stack of d branes. Why not? So instead of the proton, the idea is to consider a stack of n d3 branes. And instead of the electron, let's think as some flying closed string, for example, that is passing by this stack. And so we would have this picture where we have the stack of d branes here. There are n d branes. And then there is a closed string that is coming here and approaching this stack of d branes. And then it will go out here and get out of this stack of d branes. Now, what does it do, this string? It approaches. Eventually, this point could touch here. Now it can open up. It can reconnect. Now it's flying on the d brane. It's an open string now. And it can propagate on the d brane. And it could then do these kind of things that we saw. The string could split into two strings that can propagate. Then they can reconnect again and move like this. And eventually the endpoints are close, and then they are very close, and then they fly apart. Okay, where this would be. Here I'm representing time, a movie of the particle going here. Or equivalently, if I try to draw it in a more two-dimensional notation, I could have something like this. I have my closed string. It interacts with my d brane, and then it gets out. This is one possible diagram. Plus, another possibility is the string comes. It draws something more similar to this. It interacts here, and it goes out. But here, if I can draw it, it's something like what I drew the other day. You see, so there is this. Right? You see that this is the same as that, right? There could be other things, like the string could do this, interact once, interact another time, and then leave. In the process, the string could have holes here, right? It could have some genus, it could open and split, etc. And we would have all these possible interactions with the d brane. Like here in the electron, we have all possible interactions with the proton. And so the question is, can I then sum this all up and replace this instead by the string that moves in a non-trivial background? This closed string that just moves in some non-trivial background. Perhaps still splitting sometimes and joining, but moving in some non-trivial background. And so thinking in this point of view here of the interaction with the d brane, this would be the point of view A that we know is governed by n equals 4 super Yang-Mills, and we'll be a little bit more precise in a second. But we know that the dynamics of this stack of branes, right? All these open strings interacting there, that's what n equals 4 super Yang-Mills takes care of. And here, we would replace it by B, which is some effective closed string theory that we are after. This point B. Right? So more precisely, so in A, from the point of view A, where we think in this direction, we think of more in this direction, right? Then we think that we have open strings. These open strings that are propagating in time. Right? They draw, when they move, they draw our favorite path diagrams. And this will be described by what? Well, if it's a bunch of strings here, it will be described by Yang-Mills theory plus some massive open strings. It's not just glue ones, but there could be also massive open strings. And because we insert something on the brain and remove something from the brain, we would have plus some sources. Right? To inject, to touch the brain and remove the brain. Now, in B, however, from the point of view B, we want to think in this direction, where instead we interpret these interactions with the D brain like this as a closed string, right? That is being emitted. Right? So that same picture up there I could think as a closed string that is emitted here, drawing this closed string, or as an open string that is propagating from left to right. So this would be the point of view B of sending this closed string, and here this would be the point of view A. And this would be thinking more from the point of view B. B propagates like this, and A, we think of it in the other direction.
In the B case, there are no strings. The B scenario is some background, some non-trivial background, and then there is just the closed string.
At the very end, yes, but we want to understand how that background is generated. So if you think the D brain, you can think in two ways. It's the object that supports open strings, or it's the object that emits closed strings. Right? So there was here, you have a closed string in red. It came from where? From the D brain. So the D brain sources closed strings, or it allows for propagation of open strings. The fact that you can think from one or the other is this open string, open closed duality that I described in one of the lectures. Now, this, of course, thinking of this as a closed string insertion is like thinking that I have my worldsheet and I insert some vertex operator here. I'm putting some kind of closed string. And we are not interacting once with this D brain. We are summing over, imagining that we have many of these interactions. Let me put a circle indicating that what a vertex operator does is it creates some state that if I cut that state open, then that's the closed string. So I could sum over a bunch of vertex operators like this. That would have a net effect, if I sum over a gas of such vertex operators, of giving me something like some exponential of the integral of some vertex operator over the worldsheet. So this picture here, this would be, what I'm imagining, is some kind of condensate of gravitons. Closed strings, in particular at low energy, are gravitons, like we saw. And so this would be like saying put many, many gravitons, they kind of condensate, and they create this gas of many, many vertices that exponentiate and effectively shift my action. So this, it's in the exponent, so it effectively shifts the action. In other words, it changes the action of the string, so it gives me a new background. And this would then be the picture B, where now I have my string, and instead of considering all the brain, I think that all these interactions with the brain should be possible to resum, and now I have some closed string in a non-trivial background. Okay, and so the obvious questions that we have here is, there are two obvious questions, one here and one here. One here is what is the analog of this background V of R, schematically V of R, of course, what is this background precisely? And here, what is the effective field theory that describes this D-brane? So this question we know already, and I'm just going to remind you that it's n equals 4 super Young-Mills, and the purpose of today is to figure out what would be this potential. Okay. At this is the point where we would answer this question that Anna asked at some point. Why do we put many D-branes? It's precisely because we want to have the chance of having this picture, where we can either think of them as changing the background, and for that we need them to be very heavy, or we want to think of them as being the endpoints of open strings where we have this gauge theory description. Okay. So let's continue here. I forgot, the cutoff today is sharp, or there's some flexibility? There is a lecture at... Okay. Okay. So now the idea is, so let's think of A first, a little bit more. Just to remind you that what do we have? What is the action describing the picture for that stack of branes? There is some action for the bulk, which is just gravity. There is the action for the brane, that is n equals 4 super Young-Mills, and there would be some action for some interactions between the brane and the bulk. So this bulk action is just would be just gravity plus massive modes, massive closed strings, and so it would be something like 1 over g Newton, that we can write in some convenient way like this. Newton integral of square root of gr, which would be equal to some integral of theta square after I rescale plus some kappa h dh plus etc. And just to remind you that this stuff here is going to be irrelevant at low energy, just because this kappa is dimensionful. And gravity will decouple. That's what we already saw once. Similarly, this action for the brain is n equals 4 super Young-Mills. Here we also have plus higher derivative corrections that are also irrelevant at low energies. These higher derivatives, these higher curvatures just come from integrating out massive modes. So then you get not only Ricci, but Ricci square, Ricci cube, all these powers of Ricci that have more and more derivatives in effective field theory that we don't care at low energy. Similarly, here we get n equals 4 super Young-Mills plus, but again, if you do it precisely, it's not just n equals 4 super Young-Mills. You would get some effective theory that would contain some f to the 4 plus, etc. You get some other terms, not just f square and so on. Again, that would come from integrating out all the massive modes. All this stuff here is also irrelevant at low energy. And the coupling is also irrelevant at low energy because gravity couples to our low energy systems. The coupling of gravity is not important. And so what we conclude is that if we take our system A and consider low energy, this is going to be key. We consider low energy. We see that the system A, again, I'm being very fast because we already did this once, is equal to n equals 4 super Young-Mills in 4 dimensions plus decoupled 10 the supergravity. Yeah, that's it. Yeah.
The renormalization comes from the fact that delta diverges, so the correlation function of lots of the fields are going to be 0, right? I have delta equal to j from that diagram. I can see it in IR, otherwise is delta going to be diverged, right? From that diagram.
No, you mean, so this here, this f to the 4, this has dimension 8, right? So it's irrelevant. Right? Even at weak coupling, I mean, it's immediately irrelevant.
If we think about that diagram, if lambda increases, it means we are going to IR, right? Lots of fields have divergent.
Wait. Why lambda increasing is going to IR?
It's not equivalent.
Lambda is here. Lambda is a coupling. There's no beta function. It's up to you. It's a marginal coupling. You can choose whatever you want.
But when we want to go in IR, we need to integrate out lots of diagram, right? It was just my intuition that if I consider lots of terms, I don't know. Yeah, it's maybe wrong.
Yeah, here we are always in a CFT. The 2-point function is always 1 over distance to the power delta. It's just that delta depends on what coupling you have. If you turn off the coupling, you get this delta. If you turn on the coupling, you get this one. But I wouldn't say that one is more IR than the other. Now, this description is easiest for small coupling. Right? If the coupling is very small, gauge theory is perturbative, and we solved stuff, right? That's when this description is it. Okay. Now let's switch to B. So A, yeah.
What exactly is supergravity definition?
Supergravity is just a 10-dimensional gravity. The 10-dimensional gravity, that is the strings that are flying far away from the D branes in 10 dimensions. But it's super because when there are gravitons and the partners of the gravitons under supersymmetry, so there are a bunch of massless modes that are flying around in 10 dimensions.
So it's just the 10-dimensional case that we were talking about.
That's right. the same 10-dimensional. No, the 10-dimensional, the closed strings. We were talking about the open strings, right? We started with 10-dimensional. That was super Yang-Mills. The analog for gravity is supergravity that I did not write down, but it's Ricci plus its supersymmetric completion. Okay, but it's decoupled. That's what's important. Now, we think about B, about the point of view B. And so you want to ask, what background does a stack of D branes generate? If you put a stack of D branes, what background does it generate? And so you put a stack of D branes. And you want to ask, what's the low energy limit from the closed string point of view? So now you ask, what background does it generate? And you solve Einstein equation with a source that is a plane. So you are going to write the low energy effective action. And you are going to solve the Einstein equations that follow from string theory. And you get that the metric for a stack of branes, okay, is equal. Again, let me just write. This is found. You find this by solving the general relativity equations that themselves follow from the string effective action. That itself follows from either matching closed string amplitudes or imposing that the beta function of the two-dimensional string is equal to 0. So when you have a string theory that's moving in a two-dimensional background, it cannot move in any background. One background is flat space. But you can try to put on another background. So you write a sigma model where you couple the string to any background, right? And then that sigma model, that background is like couplings for the string, right? Tells you how the various fields are coupled to, right? Instead of just dx dx, you have dx dx with some couplings behind, which are the background. Now, those couplings would in principle have a beta function. And if you impose that the theory is a CFT and the beta function is 0, you show that these backgrounds obey Einstein equations. Right? So that's how string theory predicts Einstein equations. Equivalently, you can say, I don't want to do that fancy stuff. I just want to write what action reproduces the scattering of gravitons, for example. So what do? I study in string theory the scattering, which is just some correlation function of vertex operators. I compute it. I take the low energy limit. I get some numbers, and I write down an action that matches those numbers. And I compute many, many amplitudes, and I write more and more terms in my action, and then I resum, and I get some effective action. Then that effective action is just Einstein plus some other terms. And when you compute the Einstein equations, you can solve and now get the background. Okay? Again, this is stuff that you are taking string theory. There is no string theory course. There is kind of a string theory course. Anyway, if you were to study chapter 1 of Green-Schwarz-Witten or Polchinski, that's a standard thing that this beta function equals 0 or matching of closed string amplitudes is the standard way of deriving Einstein from string theory. And so when you compute this metric, then you solve. It's a simple problem where you have some orthogonal directions xm and some directions here x mu, and you have to solve putting some delta function source for a bunch of D branes here. So it's like solving for a Schwarzschild metric, but instead of having a point, you have a plane and so on. So you solve it, it's not complicated, and you get the following. You get eta mu nu, dx mu dx nu. That's nice. Dx mu dx nu. So that's nice. There is translation invariant in this plane. That makes sense. There is also a term which is dxm dxm. That makes sense. There is rotation in this 6-dimensional plane, right? So this mu runs from 0 to 3. This m runs from 1 to 6. And then the fact that you are solving for this background, there is some term here that is square root of 1 plus L to the 4 divided by R to the 4 plus, and here there is square root of 1 plus L to the 4 over R to the 4. That's the analog of this blackening factor in Schwarzschild, 1 minus 2 pi m over R, where R is the distance from the d-branes, so it's square root of xm, and L is related to the charge, to how many d-branes there are. So L to the 4 is equal to G string times n times 4 pi alpha prime. If you put many, many d-branes, right? Yeah, it's like having a big mass, a big charge. If you put 0 d-branes, then you drop this term and you get flat space. Right? So if you turn off, so you need n to be big. If you send this G string, you can think of it as G Yang-Mills squared, the G that appeared in n equals 4. And this thing here would be the 't Hooft coupling. And if you want this coupling of string to go to 0, you want to take this n to infinity with this 't Hooft coupling fixed. If you want to have it to be in the regime of perturbative string theory, then you want to take this 't Hooft limit that we set. Otherwise, this L would go to 0 and it would go back to flat space. In other words, if you don't put many branes, they are probes. They don't change the geometry. But if you put many, they start back reacting and the geometry gets deformed in this way. Now you see here that this description, we can already anticipate that whatever is going to come out here, this is going to be easy to deal with for lambda much bigger than 1, which would mean that L is large. And we have some small curvature. We have some things change over R big. Therefore, gravity is optimal when this L is large. Right? You want things to take a long time to change.
So why is it easy for lambda much greater than 1? We were keeping lambda fixed and taking different limits to.
This L being large means that the effective size of the geometry, which is L, right? It's by when you start seeing modifications of the geometry, is big. And so that means that this L is big, but it's big in what units? Alpha prime squared is the string length square, right? So this is saying that this length is big in units of string. Like you have some small string, some fundamental scale, and this length is much bigger than the typical length of a string. In other words, the curvatures are big, and therefore the string has some effective description. If the curvature was very small, the background would change at very small scale. It would be a very stringy background, where you would start putting the curvatures very small, and you could excite small strings. Right? So the curvatures, the length scales become very large, therefore as large. So L is many string lengths. Right? Okay, so we have these backgrounds that we are now going to analyze. So let's look at this background. and say, let's study this background at R much bigger than L, which means far from the brains. And then let's study this at R much smaller than L, which means close to the brains. So first, if R is much bigger than L, what do we get? What happens to the metric if R goes to infinity? Right, that makes sense. There are the brains, you go very far away, you see flat space. So if we go very far from the brain, we get flat 10-dimensional space-time. Right? And so here, very far away from the brains, we have, if we think of low energy, we have 10-dimensional supergravity. Again, we are always thinking about low energy. So at low energy, far away from the brains, there is gravity going around. Right? Now comes the fun part. Let's now go close to the d brains. So if R is much smaller than L, what happens to this metric? It becomes the following. Then ds square. Now it's the opposite. In the square root, instead of keeping the 1, I keep the other term. Right? That's the one I like. Now it's not 1, but it's the other term. And we get R square over L square eta mu nu dx mu dx nu plus, and then there will be L square over R square from the second square root. And now let's go and write that in radial coordinates. So we get dr square from the 6 dimensions, right? Plus r squared times the sphere. So the r square cancels the r square, so we get plus L square times the geometry of a 5 sphere. Right? So this was just a clever way of writing the 60 part of the action. I just split radial part and angular part, right? Is it okay? It's dr squared plus r squared, the sphere. Now here, we see that this space, this is a sphere. It's an S5. And what is this space here? Well, this space here, you might not recognize yet, but if you write R equal to L over Z, then this becomes eta mu nu dx mu dx nu plus dz square divided by z square. Maybe there is some L square here, but that you can just absorb by rescaling x. And what's this metric? ADS. And so this part is just ADS 5. And so we find this background ADS 5 times S5. Right? So close to the D brains, we see this ADS 5 times S5. Now we want to ask what happens at low energy. Right? But now we have to be very careful. Because what do we mean at low energy? We mean we are an experimentalist. And so what energy? Because here we are in a curved space-time, there are many energies. It depends where we are. So we are the experimentalists. The brains are here, and I'm here at infinity doing some experiment far away from the brains. Right? So the energy I want to consider is the energy of the observer at infinity. Right? So let's do the following exercise. Let's suppose this is infinity, and we are here. Right? And we want low energy. Right? We want to see low energy. What do we see if we want to see low energy? First, we see this. We see flat space, supergravity. But what else do we see? So for that, let's imagine, let's remind us that we see that, let's suppose that we have a friend here that is carrying some very energetic thing. Right? Some huge energy. Right? It's a box with an atomic bomb, I don't know, something very, very energetic. And then this person is going to walk close to it's going to walk far inside, close to the D brains. So we stay here, and he or she is going to go far away. And eventually, they reach here, are very small. Now, what do we see? What I'm representing is what we see here at infinity. So let me put in blue, and let me put this explosion in blue. That's the energy that I see nearby. And now, what do I see when I'm looking at this and seeing what energies are they carrying? Now, for that, let's remember that we have, if I look at my line element, for me, my delta time square measured by observer at infinity is equal the metric to the proper distance at infinity, that it's just ds squared, right? My proper time. But here, close to the D brane, when I'm close to the D brane, time gets shifted by R over L. Right? So delta T at infinity is equal to R over L times delta T, the proper time for the observer close to the D branes. Right? So what he sees as 1 second, I see as if it's 1 second for him, for me it's much less than 1 second. Right? There is this R over L. And so, right.
That R is the place of the person near.
No. Sorry. There's something wrong here. Proper time. No. Sorry, I'm wrong. It's the opposite. It's -1 here. L over R. Right? Because the time at infinity is dt, right? And the proper time is R over L times dt. And so the proper time, right, which is ds squared, is L over R times the time at infinity. I was worried, yeah. So 1 second for him takes a long time for me. And in particular, the energy measured by me, it's the inverse, right? Time and the energy are conjugate, would be R over L times the proper energy. Now, someone carrying the box with this atomic bomb is close to the atomic bomb, right? Locally, I'm walking with my atomic bomb. I always see my atomic bomb, right? Locally, for me, I mean, there's the equivalence principle, right? For me, I'm always seeing my atomic bomb. So the proper energy for me that I'm carrying the atomic bomb is always the same. But for me that stays here at infinity, this is becoming dimmer and dimmer. And eventually, for me, this atomic bomb is low energy. So for the observer at infinity, anything happening close to the brains is low energy. Right? So for him, anything near the brains is low energy. And so finally, we conclude that for the observer B, at low energy, we get anything, which means I have this background near the brains. So I have ADS5 times S5, everything, not just the lowest modes, not just gravity, but everything. So ADS5 times S5 superstring theory. The full theory with all possible massive strings, everything, black holes, everything you want in ADS5 times S5. Or, that's one option, or I have 10-dimensional supergravity. And the claim is that as before, they decouple. You have either this 10D supergravity or you have ADS5 times S5 superstring. Now, why would they decouple? So now here we can remind ourselves what happens if I put some strings moving in ADS5 times S5. Right? So I have this near geometry, which is ADS5 times S5, and I put a bunch of stuff there. And now you remember from the tutorial, ADS5 times S5, this geometry is like a box. Things don't get out, right? So things, if you put them there, you can throw them away and they go and they bounce back. So things that you put inside ADS5 times S5, this space-time, which we can think as this cylinder, the inside of this cylinder, is effectively like a box. That if you send some closed strings, they move and they come back and they oscillate here, but they don't get out. And so whatever you put here inside this box stays inside the box. And that's how you don't need to take these things and mix them with the stuff far away. Equivalently, you can ask, what about low energy degrees of freedom here? Would they interact with the stuff here? And the answer is again no, because low energy stuff here will have a very long wavelength. And this ADS is like a box. And so it's like measuring some microwaves with your radio antenna. So what happens is that the absorption cross-section for stuff from outside to go inside decays with the frequency and it will fade away. And so in practice, you have this decoupled system. So they decouple again. Because stuff inside the box stays inside the box, and long wavelength stuff outside the box is not absorbed by the box. And so we conclude that this is another low energy description of the same stack of d-branes. And now we can equate A and B there. And if we equate A and B, you conclude that 10D supergravity shows up in both sides. So you can basically, if you equate both, you can cross them out. You equate both A and D, you just cross out 10D supergravity. And we conclude that 4-dimensional n equals 4 super Young-Mills, the full theory, is equal to type 2B 10-dimensional superstrings in a 10-dimensional background, which is ADS 5 times a 5 sphere. And this is ADS, and this is a CFT, and this is what is called ADS CFT. So next time, we will make a few comments about this duality, about how the matching of parameters go, and we'll try to make one check of this duality. It's a conjecture. It's not a proof, because what I told you is cannot be seen as a proof. I mean, there were many steps that were kind of hand-wavy, right? Like crossing gravity out and stuff like this. It's kind of, but it leads to a very precise prediction, right? This sum string theory is not a random string theory, right? It's really type 2b in ADS 5 times S5. And so it says that these energies are not any energies. These are energies of strings in ADS 5 times S5. And whatever I compute from the gauge theory, I should be able to compute from the string theory and vice versa. Now, it's going to be a challenge because this theory is easy when the coupling is small. This theory is easy when the coupling is large. Because coupling large here means you have an ADS with a big curvature. You have a big radius ADS. You have like a big sphere and a big hyperboloid and small strings moving there. That's easy. But here it's easy when lambda is small. That would correspond to a very curved ADS where the strings are huge, and so strings would be hard. So when this theory is easy, this is hard. When this is easy, this is hard. So that's a curse and a blessing. It's a curse because it's very hard to check if it's true. Because when you can compute something here, you cannot compute there, and vice versa. But you can say it's a blessing because it allows you to compute things that you could otherwise never compute. Because if you really trust the duality, you can compute things here that are telling you something trivial here, it's telling you about very quantum strings here. And something trivial here, it's telling you about strongly coupled quantum field theory. So we have to see it both ways, and that we are going to start with some comments about how we can think of ADS CFT next in tomorrow's last class. And then we'll try to do a check. And about can we do some non-trivial check that is not just symmetries, but really dynamics that would say, wow, it's impressive. We believe probably this is okay. And that's what we are going to do next time. Okay.